Okay, so the plan for today is to talk about these two algorithms, the Deutsch and the Deutsch-Josa algorithm. So first, I just like to start with a trick that we use in quantum algorithms, which is called as the phase kickback trick. Okay, now remember that last time we already talked about developing the superposition of the input-output pair. Today, what we'll do is we'll sort of tweak it a little bit and we'll see how to encode the function output actually in the phase or in in the exponent, you'll see. So let me just jump right into it. So let me think of f as a Boolean function. Okay, good. So let f be a Boolean function. Okay, so just 1 bit outputs. As I've alluded before, this is typically good enough. Like if you have a multi-bit output that you're interested in, then you could just have many functions computing each output bit. Okay, and recall that we already talked about evaluating a regular classical function using a quantum circuit, and we said that we will represent this in the following way. I hope that everyone remembers this. Okay. So this is going to be a unitary transformation, and this sort of this ancillary bit b is going to carry the function output, right. Now obviously when b is equal to 0, right, I get x f x, okay, this is just by property of XOR, and when b is equal to 1, I get x 1 XOR fx, which is basically flipping the output bit, right. Okay. So more concisely, okay, good. More concisely, I can say that for any b, okay, Cf of x b can be represented as x minus 1 to the b f x. Convince yourselves of this. Okay. So when b is 0, minus 1 to the 0 is obviously 1, and otherwise it is minus 1. Okay. So this is good. I mean it's really doing nothing, it's just coming up with a neat way to write down what you get. Okay, now what I am going to do is I am going to make things more interesting by saying swap b with the minus state. So this is this state, right. Okay, may I move on? Next slide. Okay, so I am swapping b with that. So now what do I get? Okay, so if I compute Cf of x with the minus state, then this is of course Cf of x 0 minus Cf of x 1 over root 2. By the way, so far I have largely been carrying around these normalization constants, but soon I will just start dropping them, okay, because they are not going to ever really matter too much. So this is by linearity x f x minus x the complement of f x, right. And now of course I can take this x out, so I get f x minus okay. So this is just some symbol pushing so far. Now if f x is 0, then I get maybe I will just write it down. I get this if fx is 1 then I get this. Okay, so in general I can say that Cf of x minus can be written as minus 1 to the fx x minus. Does everyone agree? Okay, and if I apply this to a superposition, so if I instead of just taking a single x, if I take the summation over all x, right, then I get summation yeah. So, this is called the phase kickback trick. Okay. So, we'll see this appear again and again in our quantum algorithms. So, what is it really doing? I mean maybe the thing to really internalize is in fact for a single x, right. So, if I apply the function, think of it as a function oracle, okay, because I don't in general want to worry about how I implement this function, like what is the quantum circuit that I use and so on. So, it's sort of a box, it's like an oracle for me. I give it some input and I get some output, right, and we discussed how this behaves. So, if I apply this oracle to x with the minus state, then what I end up getting is that the f of x value is encoded in the phase. So, I will not get into the physical meaning of this phase and so on. From the computational point of view, basically you can think of it being encoded in the sign, right. So, basically I ended up, okay, what was my input? X comma minus, right, this was my input. What is my output? It is also x comma minus, but with a sign which depends on f of x. Okay, this sign is sort of, it's capturing the phase, and I can generalize this to the superposition of all inputs. Okay, so this is going to turn out to be very useful for us. Any questions about this? So now we'll go right into Deutsch's algorithm. Okay, great. So good. So let's sort of jump into Deutsch's algorithm. So Deutsch is famous as one of the founders of quantum computation together with Richard Feynman, and he has a book that he's written. I believe it's called The Fabric of Reality. I haven't read it myself, but there is this quote of his from that book which is really famous. So what does he say? Quantum computation is nothing less than a distinctly new way of harnessing nature. It's the first technology that allows useful tasks to be performed in collaboration between parallel universes and then sharing the results. Okay, so this all sounds very cool. I wanted to show you that this is what he thinks about it. He's one of the founding fathers of this field. But I also do want to emphasize that this is an interpretation of quantum mechanics, right. So, there are many ways of interpreting quantum physics. There is one which is called the many worlds interpretation, and that is the one that I think he was inspired by, and this quotation is coming from there. So, now whether one believes in this interpretation or that interpretation, it's a free country, you can believe anything you want. I don't have any opinion on that, but what he is saying here about, you know, tasks to be performed in collaboration between parallel universes, even if we don't think of it as parallel universes, at least we are going to see this notion of, you know, performing sort of an exponential sized computation like in parallel, right, and then this sharing the results, right. So this is actually the key part which even previously I have talked about, that finally you have to measure and get something useful out of it. So how do you do that? So, you know, hopefully we'll at least see an example where you can understand what you know, what this is trying to get at. Okay, but yeah, this is still nevertheless his interpretation of it. Okay, so let's look at an actual algorithm. Now, you know, we are finally getting warmed up, right? We set up all the notation, we talked about all the formal setup. So let's try to now find examples where quantum algorithms will do better than classical algorithms. Okay, and we'll start with a very simple example right now, and we'll develop that into more sophisticated examples. The goal is to try and see what is the extra power that quantum offers. And actually there's a very interesting way of thinking about it. Maybe I'll come back to that after we see a few algorithms, it might make more sense. But basically quantum algorithms are giving you this one extra ability over classical randomized algorithms. So of course they give you randomness, but aside from randomness, they give you this one extra thing, which is, you know, a kind of change of basis, a kind of rotation. So this is something we'll see even in the present algorithm. We already saw it when we apply the Hadamard transform, right. In some sense we go to a different basis. We'll talk about this much more formally, but I'm just trying to give you a little bit of intuition. So what is our problem here? Okay, so as I said, it's a little bit of a toy problem, but it already illustrates some very nice ideas. You're just thinking of a single bit input to output function f, and you're given a promise. Okay, so these are in computer science, these are known as promise problems. So you're given a promise that f is one of two things, either it is constant or it is balanced. Now in the case of a single bit output, constant just means that, well, both the outputs are 0 or both are 1, and balance just means that 1 is 0, 1 is 1, I don't care which is which. Okay. The question that is being asked is to figure out which one of the two this function is. And what we are going to use as a sort of notion of as a measure of efficiency is actually the query complexity to this function. So remember in the previous couple of slides I was talking about how I want to think of this function as an oracle, right. So I don't want to care about how it is implemented. What I am interested in is learning something about this function. In this example, I am interested in learning whether it is constant or balanced. I'm interested in thinking about, you know, how many calls to the function do I need to figure this information out. Okay. So what do I mean by that? Now look, everybody knows we can, you know, we already saw two ways of encoding function output. One was, you know, the recent most, we saw the phase kickback, otherwise we saw the XFX, right. So now obviously even classically in this example, you can make two evaluations and figure it out, right. You evaluate it on 0 or you evaluate it on 1, of course you will figure out whether it's constant or balanced. What we will see is that this evaluation, I think of it now as a black box, as like an oracle call. Okay, so for those who are not familiar with this sort of terminology, right. So oracle just means that well, there's some cloud in the sky, it's magical. This is not my idea. So some people are smiling. It's, it's very common in cryptography. There's a cloud in the sky, I give it some input, okay, I get some output. This is what I mean by oracle. Okay, and this is what, well, the community means by oracle, which I am reporting to you. So we are going to think of how many queries do we make to this oracle, and in the classical setting we need to make 2 queries, and what we will see is that in the quantum setting 1 query will suffice. Okay, now this may not seem like a very big improvement, but we will generalize it. So let's get started. Okay, so good. So how should we compute this? So let me show you. So I am going to show you the algorithm, in a picture format. So this is my CF, right? And as I said, I want to think of how many inputs and outputs, how many inputs I kind of query this with. So what we'll do is we'll take 0, apply h, okay, and feed this to the function. Okay, let's call this x. Now we will also take 1, apply it to h and feed this to the function. We will call this y. Now what we saw earlier is that what the function does is it gives you x and y XOR fx, right? This is how our function is behaving. In case you have forgotten this, just assume it for now. Okay, for now the way we do this does not matter too much. Okay, and then what I am going to do is I am just going to apply the Hadamard transform once again to the top bit, and the bottom bit I keep it unchanged. So I am going to call this state as psi 0, this one as psi 1, this one as psi 2, and this one as psi 3. Okay, so this is my circuit that I am going to implement. So this is my algorithm. And of course, I will perform a measurement in the end, we will see what that is. So now let us analyze what is happening over here. So what is, okay, so psi 0 is just 0 comma 1. What is psi 1? Well, it is plus comma minus, right. So psi 1 is simply plus comma minus, okay. Now remember what we saw with phase kickback, right. So this was our phase kickback. So if I apply CF to x comma minus, then I get the phase kickback, right, f of x. Okay, so now basically I apply phase kickback, or I get, rather than apply, I mean I get phase kickback, and this is because my second bit here, the ancillary one, is minus. Okay. Now I am going to consider both cases one by one. So let us consider the first case. Okay. So case 1 is that f0 is equal to f1. So in this case what happens? So now let me write down what happens after I apply CF, right. So the phase kickback gives me -1 to the f0, 0 minus, there is a 1 over root 2 that will hang around here, okay, plus -1 to the f of 1, 1 minus, right. Everybody agree with this? Make sure that you stay with this derivation. So, I mean we're not doing anything. So, all that we are doing is applying the phase kickback linearly, right. So, I have 0, right, because my plus obviously is a superposition of both zeros and both 0 and 1. So, I am just looking, this is just the plus, right, and this is the minus that is in the ancillary bit. Okay, and so I am just getting, after the phase kickback, I will get -1 to the F0 for the first term and -1 to the F1 for the second term. Is that clear? Okay. Yeah, I guess I already said this. So now this is the case where, you know, f of 0 is equal to f of 1. So that means I can take out the -1 to the whatever value it is, right. So I can write this as -1 to the F0 0 plus 1 over root 2 minus, okay. So this is nothing but -1 to the f of 0 plus minus. Everyone agrees? Okay, now on the other hand, if f of 0 is not equal to f of 1, then one sign will flip, right. So then I will get psi 2 as plus or minus 0 minus 1 over root 2, right. So this is nothing but plus or minus minus minus. Everyone agrees? And now go back to the algorithm. So this is psi 2 that we are talking about, right. So this is after the function evaluation. So I got plus minus or minus minus up to some sign. Now I again apply a Hadamard on the first qubit. So now what happens? So I apply Hadamard on the first qubit, right. So now I get psi 3, okay. So this is going to be good. So who can tell me, so in the first case, yeah, so if F0 is equal to F1, then we got plus here, and on the other hand, if the two are not equal, then we got minus, right. So this is the first qubit. So now if I apply Hadamard to this, what do I get? So if I apply Hadamard to plus, what do I get? 0. One of the two, right. So you can always try. Yeah, so in one case I will get 0 and in one case I will get 1, right. So psi 3 is plus minus 0 minus if F0 is equal to F1, and this is, you know, plus minus 1 minus if F0 is not equal to F1, okay. Now note that if F0 is equal to F1, then F0 XOR F1 is 0, right, else F0 XOR F1 is 1, right. So this means that I can again more succinctly write psi 3 as plus minus the XOR of the two values, right, just using this, right. So it is 0 in case 1, it is 1 in case 2, right, and in either case this is equal to F0 XOR F1. So what I managed to do is by running this circuit, right, I managed to encode in the first qubit the state F0 XOR F1. Okay, and now if I measure the first qubit, I will have my answer. So this is what I was trying to say, that you have to do some transformations in order to get something useful, that you could not get classically. Of course, here we didn't get that much of an improvement, but very soon we will. So this is just a simple 1 bit input version. We will now generalize it to n bits, and we will see that there is a much more dramatic improvement there. I want to also just call attention to this one very interesting structure that this algorithm has. It's called rotate, compute, rotate. So look at this circuit over here, right. So there is a rotate here, right. The Hadamard is nothing but a rotate. Why is that? Can anyone tell me why I am saying the Hadamard is nothing but a rotate? Exactly. That was what I was looking for. So what he said is that it's a unitary operation, right. So any unitary operation is a rotation, right. So if you think of the matrix for the Hadamard transform, and in fact for any unitary matrix, this corresponds to a rotation, and this is actually, it turns out, the superpower of quantum computing. This rotate, compute, rotate, right. So here you can already see one very simple example of it. The next example we will see is more sophisticated. It will follow a similar blueprint. Why is this rotate, compute, rotate? Well, that's what you do, right. So the step 1 which I have highlighted in yellow, this is rotate, right, and then there is compute over here, and then there is again a rotate. So first of all, when you do the rotation on the input, you manage to get the superposition of inputs, right. So this is kind of getting the parallel engine going, right. So this is what will let you compute in parallel. Now once you have the superposition, you apply the function. Of course, once again, superposition over what? 0, 1, plus, minus, what is it? That all will depend on the algorithm, but just at a very, very high level, I got some superposition. So now I can compute in parallel, right. So now whether I apply phase kickback, whether I apply the other kind of output superposition that we saw, whatever I do, I did some computation, right, and now I want to measure it in the end. Maybe in some cases, again depending on what you are trying to do, before measuring you could rotate again, and these rotations are actually going to, what we will see maybe next week, is that these are implementing the quantum Fourier transform. Okay, and even in the classical world, what a Fourier transform does is that it lets you go from one basis to another basis. So in electrical engineering, it's very, very popular, you go from the time domain to the frequency domain. And why do you do this? Because I'm interested in figuring out some information about, my function or my signal in the case of electrical. Doesn't matter, there is some long sequence of string of data, let us say, so some long sequence of bits, let us say, and I am interested in figuring out some pattern about it. Now it turns out that in some situations, right, representing the same data along a different basis gives me information about this pattern that I am looking for. And this is the broad theme of all the quantum algorithms that we are going to see, that basically by performing a sort of change of basis, right, I will represent my data differently. Is this making sense? Yeah, so I have some data. So maybe because I am basically trained as a computer scientist, this is the way of thinking that comes very naturally to me. I have some sequence of bits, right. What is that sequence of bits? Let us say, it is the output of f on exponentially many input strings. Let us say I have n bit input, right. So there are 2 to the n possibilities for inputs, and my output string is simply the f applied on each one of them, right? I am interested in figuring out some pattern about this. Now, not every pattern is amenable to a quantum algorithm, but in some cases it will turn out to be that by looking at it from a different lens, so to speak, right, looking at it via a different basis helps me to learn some information. And let's come back now to the one example that we did see, this one humble little example. Isn't that what it is doing? It is managing to encode F0 XOR F1 in this bit, right? Because of that, I am able to make one single measurement and learn something that I could not have learnt otherwise. So, I want to think of this intuitively as capturing a pattern, right? This data of F0 XOR F1, I could only access it by performing this rotate, compute, rotate, but look how nicely we managed to access it. It sort of comes and sits in the first qubit exactly in the form that I want, and now I can measure it.